So I will present you work which is still in progress with both my PhD advisors Barbara Gris and Irene Kaltenmark about decorrelation of vector field with speed of varifold. So first, I will remind some results about the LDMM framework. So given a time-varying vector field, we can generate a unique flow of diffeomorphism that satisfies this equation. And in the context of registration task, so given a source and a target, you want to find the best diffeomorphism that will deform one into the other. So this problem of finding the best diffeomorphism is equivalent to solving an energy minimization problem, which is decomposed in two parts with a regularization term and a data attachment term. So it is a measure of dissimilarity between the real target and the deformed source. And now, if we consider not one vector field, but two vector fields, in the same fashion, we can do the exact same thing. So we can generate a flow of diffeomorphism that has been generated by the sum of those two vector fields. And if we want to perform a matching task, we can then define an energy minimization problem in the same way as we did before. So if we are interested in working with two vector fields to do some registration, we would like particularly that those two vector fields are different, so that they do not have the same action on the shapes that we are working on. So we want to clearly identify the contribution of V and W on the deformation of the diffeomorphism. If we think about, for example, doing some statistics or just to have a better interpretation, we do not want that V and W overlap during the deformation. You can think about it as, for example, if V is a smooth vector field and W is like a translation, we want that that all the translation of the diffeomorphism psi is encoded in the W, or in other words, we do not want that the smooth vector field does any translation. So it leads us to consider how to decorrelate two vector fields. And more particularly, we want to decorrelate two vector fields with respect to a given shape. Because if we consider just a toy example, so with two vector fields, if those two, okay, the other side, with those two vector fields, so the vector field in red, V1, which is an horizontal stretching, and V2, which is a scaling. And I consider two shapes, just a straight line and a circle. I can define the infinitesimal deformation of both shapes in the direction of the horizontal stretching and in the direction of the scaling. So if we look at the first line, we can see that both vector fields act in the same way on the straight line. So you can see here in red, it's the deformed straight line in the direction of the stretching, and the green line is the deformation of the straight line in the direction of the scaling. And they are exactly the same. So for the straight line, both vector fields are exactly the same vector field. But if we are looking to their action on the circle, you can see we get different results. So it highlights why we need to decorrelate with respect to a given shape, because for the straight line, those two vector fields are correlated, but they are not for the circle. So in the rest of the talk, when I will talk about decorrelation, it will always be with respect to a given shape, for example, in the static or in dynamic. So now we can define a correlation level, so still with respect to a given shape, between a vector field and a space of vector fields. So this is defined as the norm of an optimal vector field W star, which minimizes this functional here. So the right term is just regularization term. And the most important term is this one. So I will define later what is delta mu qv, but we can just think about it as the speed of the shape q in the direction of v. The W star here is the best approximation of the speed of q in the direction of v with an element from W, and of projection. So now I will define more precisely what is delta mu qv here. I know you are all experts of varifold right now, thanks to Blanche, but I will still define some things. So a varifold is a continuous linear form on a space of test function. And given a shape, we can define a varifold which is associated to this shape. And particularly, for example, for a discrete curve, we can model it by a varifold given by three main components, so with centers, tangent vector, and a length. For example, if we look at the blue shape here, which is discretized with blue point, yep, varifold, yeah. So if we are looking to the blue shape here, which is discretized, we can define its varifold representation by the centers of the faces, the length of the faces, and tangent vector. To keep the thing simple, in the rest of the talk, I will always consider discrete curve. Those results are still true for continuous curve or surfaces, but the formula are not really tractable and not really nice to look at. So I will always consider discrete curve here. So some property. So if we consider a reproducing kernel Hilbert space generated by a kernel, we can define a scalar product between varifolds. It will be useful, for example, to define a metric between varifolds to measure distance. And diffeomorphism can act on a varifold in this way. So the action of a diffeomorphism on a varifold is just we build the varifold on the shape phi of q. So now we can define the speed of a varifold in the direction of a vector field. So we consider a flow of diffeomorphism, and we compute the derivative of this, the action of the diffeomorphism on the varifold with respect to time at time equal to 0. In the ID, it's almost the same thing when we consider the diffeomorphism that acts on a shape Q, and then we define the infinitesimal action by taking the derivative. Here we can think about it the same way as the infinitesimal action of a vector field on a varifold. This expression is divided in three terms. So first, it's a variation of the length. Second term, the variation of with respect to the position in the direction of the vector field. And finally, variation with respect to the tangent space in the direction of v. And this expression that is named speed of a varifold is delta mu qv I told you about before. So if we go back to the correlation level, now we know a little bit more about what is delta mu qv and delta mu qw. And as I said before, we can have a metric on the speed of varifold if we use a reproducing kernel Hilbert space. For instance, we'll use Gaussian kernel, and Gaussian kernel needs to have a parameter, so the size of the kernel. And depending on the size of the kernel, we can have different results for the optimal vector field that we will obtain in the end. So if we consider just this example, where the original shape is a blue peanut here, and we consider a fixed vector field in green here, so 2 and v are the peanut and the green vector field. So we can consider the deformation of the shape in the direction of the vector field here, of the vector field in green. This vector field is built in the way that he will translate the lower part of the peanut, just a pure translation. The upper part will be a translation with a stretching. So if we do the infinitesimal deformation, it will give us this, this red curve. Now we want to compute the optimal translation. So what is the W here, which is a translation, let's say, that minimizes this distance? In other words, what is the translation that imitates the best, the red curve here? If sigma is really small, the optimal translation will align the barycenter, like a classic translation. If sigma is higher, is bigger, so more or less the size of the shape, we can see that the optimal translation will align the lower part of the barycenter. So in this case, it will be more consistent to have this kind of sigma, since half of most of the vector field in green is a translation as in the lower part, so it will be consistent to have the optimal translation to match the lower part exactly, and not the barycenter. And if we look at sigma that tends to infinity, so the kernel is degenerated, so there is no reason to move, and the translation is equal to 0. So now it was some example in static. So I motivated the talk by registration. So we need to do some dynamic. So the global problem that we are looking at is given two spaces of vector field, we want to minimize this energy, so matching task. In the literature, there are different approaches to deal with two space of vector fields and dynamic. Here, I will present two approaches. So one, which is LDDMM-like method, and another one, which is a semi-direct product. So first, as I presented before, if I consider a flow diffeomorphism generated by the sum of two vector fields, and I consider the source Q0, I can define a deformed shape, and I have an energy minimization problem associated to the matching task. Since I only have one shape, I can define a variable which is named costate or a moment, which live in the cotangent space, cotangent of the shape space here. And we can parameterize this problem with only one variable, which is our moment P. So now, what do we want to do? It's to decorrelate V and W. So we will add the decorrelation as a penetration term in the energy, like that. However, if we want to perform a decorrelation, V and W are parameterized by only one and the same moment. So they are kind of related, even though we add this correlation here. We can see that with some simple example. If I want to match this blue line here to the red curve here, either I have a degenerate result, so my shape will shrink and nothing will come out, or we have a result that doesn't make any sense, it doesn't match correctly, and in green, it's a smooth vector field, and it goes up and down. That's really what we want to have here. So we want to have a second moment, the second moment, one for the vector field V and one for the vector field W. And to do so, we consider the partial gradient with respect to V and W to extend the possible trajectories of the minimization problem. So now we have two moments, so one for V and one for W. They are different. So we gain 1 degree of freedom to, so we have a problem which is more flexible to do some decorrelation. So I will take the same exact example. So we have a straight line in blue and a target, which is a curvy straight line. So I built the red curve by translating the blue one with a translation of 2, and I added a small curvature. So the optimal translation that I want to have with a model with V is a smooth vector field and W a translation is that the translation is equal to 2. That encode all the translation of the model. So if I do not put a decorrelation as a penetration term in the energy, I see that the optimal translation I get is about 1.4, 1.4. So it's a bit far of the 2 that we wanted to have. And here, the black arrows represent the smooth vector field, so the vector field that we do not want to do some translation. But here we can see that if we do not take into account the decorrelation, the smooth vector field is vertical, so it will do some translation here. Now, if in the energy I consider the decorrelation, I have way better results in the sense where the translation is about 1.9, 1.9. And the smooth vector fields are only in the direction of the curvature of the target. So the deformation is decomposed in the translation, which is almost 2, and in a curvature of the target. If you look at the dynamic, it stays during all dynamic pretty orthogonal to the curve. The second model, so the semi-direct model, is comes from another project, which is a joint work with Thomas Piron. So we consider here a finite dimensional Lie group and the Gothic G its Lie algebra. So here the Lie algebra, we can consider it as a W in the previous model. So the Lie group acts on the space of diffeomorphism, and we can act, the semi-dot product act on the shape space so that we can define some deformation and some dynamic. So we can do some registration task, and same as before, same equation. We have a problem with one shape, so we can parameterize by one moment. And we still have the same problem. We have two vector fields with only one moment. But if we want to decorrelate, it won't work because we lack a degree of freedom. In the previous model, so the direct model, to add a second moment, what did we do? We consider the partial gradient of the energy. Here, we will consider a different approach. We will define a new shape, field Q, by this little change of variable. So in the ID, we take our original shape Q, and we remove the action of the Lie group on this shape Q. And if we always think about the matching task, if I consider source object Q0, then the dynamic deformation of field Q is just the source deformed by only the diffeomorphism, not the Lie group. So when we do that, we can consider the augmented shape space. So now we do not have only one curve, but we have two curves. One which is the tilde Q, so the curve without the Lie group. And the other one, we consider that the part of the Lie group is also a curve. Since we have two curves, we can have two moments, and we can do some decorrelation because V is parameterized by one moment P, and X is parameterized by P Gothic G. We have two vector fields, two moments, so the correlation should work normally. So I take the same example as before. We are still doing matching task. Without decorrelation, we have the same thing. So the smooth vector field will participate in the translation. It's not what we want here. And if I add the decorrelation in the energy, the result is still way better. So a translation almost about 2-2, and the vector fields are orthogonal to the shape, so in the direction of the curvature of the wide one. And it stays orthogonal during all the dynamic. So as I said before, it's still a work in progress because we need to try with more complicated data, more complicated deformation. In this framework, the two model give the same results. One possible reason is because the data are too simple, so they do not need to have complex structure to deform it and to keep the correlation on. So we need to explore more in this direction. Thank you. And some references. Like of doing it, for example, if you want to do first a translation and then, in some cases, it can be useful because it's, I think, what is done in a lot of computational code right now. But if we think about the two peanuts, for example, if we just align the barycenter, it will not, the best translation is not just aligning the barycenter. Sometimes we want to align just a part of the shape. So we need to have the information of what the other vector field is doing in order to compensate the action of one with the other. So that could be a reason. Yeah. So the formula for be here. Okay, yeah, so this is a correlation formula, so it's decomposed with like just a regularization term. So we need this to ensure the existence and unicity, because for example, if we think about V, which is like smooth vector field, and W a rotation, if Q is a circle, any rotation will preserve the circle. So there are an infinity of possible rotation, sorry. So to ensure unicity, we need to have this second part. And this part is just like kind of orthogonal projection of the speed of varifold on V and W. That's the way it's built here. So W is a vector field, so it depends on what context you want to use it. So geometries, multiscale, or modular, the deformation framework like Barbara does. So, oh, they are different? So, in practice, is the fact that so to build this direct model, for example, with two moments, we cannot really define an Hamiltonian to this. So this is not really something that comes from direct calculus. That's why I say it's LDMM-like, because it relies on an LDMM framework, but we decide to expand the possible trajectory. The other model, the semi-direct model, is more a structured one, where like the two momenta come from a change of variable, and the semi-direct product will take the information of the Lie group. It's an action of the Lie group on the diffeomorphism. So in the dynamic of the diffeomorphism, you can see after, of the shape, sorry, it will take into account the Lie group here. So it's more about how the two parts interact between them. Okay. Right here, like here, we can say that the equation on the Lie group part is only about G. Here, it depends on the diffeomorphism, so it's kind of integrated between both of them. Not the case because we only have one shape on the first and the direct model. Thank you.